Welcome to G Fun Facts Online, where we dive deep into the most mind-bending corners of science. Today, we're venturing into the quantum realm, a place where the rules of physics as we know them get seriously weird. Imagine cooling something down, way down, to just fractions of a degree above absolute zero, the coldest temperature theoretically possible. At these extremes, a completely bizarre state of matter can pop into existence, the Bose-Einstein Condensate, or BEC for short. And within these ultra-cold clouds of atoms, things can get even stranger. We're talking about superfluidity, fluids that flow with absolutely zero friction. Zero. This isn't a page from a sci-fi novel. It's a real frontier of modern physics that continues to blow scientists' minds. So where did this wild idea come from? Our story kicks off in the early 20th century. Back in 1924, an Indian physicist named Satyendra Nath Bose was exploring how photons, particles of light, behave statistically. He sent his groundbreaking work to none other than Albert Einstein. Einstein, being Einstein, immediately saw the massive implications. He took Bose's ideas and applied them to atoms, predicting something extraordinary. If you could cool a gas of certain particles, now called bosons, to incredibly low temperatures, they would all collapse into the lowest possible energy state. It's like they'd lose their individuality. Their atomic wave functions would overlap so much that the entire group of atoms would start acting as a single quantum entity, a superatom. This predicted state was named the Bose-Einstein Condensate. For decades, BECs were just a cool theory. The big hurdle? Reaching those ridiculously low temperatures without the atoms just freezing solid or vanishing. But science loves a challenge. The breakthrough finally happened in 1995. Eric Cornell and Carl Wyman at GELA, an institute in Colorado, were the first to successfully create a BEC. They used rubidium atoms and cooled them to an unbelievable 170 nanokelvins. That's billionths of a Kelvin. Just imagine how cold that is. Shortly after, Wolfgang Ketterle at MIT did it with sodium atoms. This wasn't just a small step. It was a giant leap that earned Cornell, Wyman, and Ketterle the 2001 Nobel Prize in Physics. A whole new chapter in atomic physics had begun. Now, while BECs were being theorized, another quantum puzzle was baffling physicists: superfluidity. This was first spotted back in 1937 by Piotr Kapitsa and independently by John Allen and Don Misner. They found that liquid helium-4, when cooled below about 2.17 Kelvin, known as the lambda point, started doing some really weird stuff. It could flow through tiny tubes with no resistance at all, zero viscosity. It could even climb up the walls of its container and escape, like something out of a horror movie for tiny particles. Kapitsa called this state superfluid. A year later, in 1938, Fritz London was the first to link superfluidity with Bose-Einstein condensation, suggesting that the bizarre behavior of helium-4 was quantum mechanics showing off on a macroscopic scale. It's important to remember, though, that while they're related, not all BECs are superfluids, and not all superfluids are BECs. But these dilute atomic gases that form BECs? They give us an incredibly clean and controllable way to study the basics of superfluidity. So how does this frictionless flow even happen? The answer, as always in this realm, lies in the weird and wonderful rules of quantum mechanics. First, think about the wave nature of matter. Yes, atoms can act like waves. At ultra-cold temperatures, the de Broglie wavelength of these atoms gets really large. In a BEC, these waves overlap so much that the atoms basically lose their individual identities and behave as one big, coherent quantum wave. Then there is Landau's criterion for superfluidity. Soviet physicist Lev Landau came up with this. He said a fluid can be superfluid if there's a certain critical speed. Below this speed, it's just not energetically worth it for the fluid to create any disturbances, like tiny sound waves or other excitations, as it flows. If no disturbances can be created, there's no way for energy to be lost, and voila, no friction. Interestingly, for superfluidity to actually happen, the particles need to be interacting with each other. Another cool sign of superfluidity is quantized vortices. If you stir a normal fluid, you get swirls and eddies that eventually die down because of friction, right? But if you try to rotate a superfluid, it can only do so by forming these tiny, perfectly defined whirlpools called quantized vortices. Their spin is quantized, meaning it can only take on specific, discrete values. Scientists are super interested in how these vortices behave, especially in more complex condensates. And get this, second sound. In most stuff, heat just spreads out. But in superfluids, heat can actually travel as a wave. This is called second sound. It happens because of the interplay between the superfluid part, which carries no entropy or disorder, and the normal fluid part, which is made of those excitations and acts like a regular viscous fluid. In fact, just in February 2024, physicists at MIT managed to capture direct images of second sound in a superfluid gas. That's a huge deal for understanding how heat moves in these exotic systems. Creating these BECs and seeing superfluidity in action is a serious feat of engineering. Scientists usually start with a dilute gas of atoms, often alkali metals like rubidium or sodium. It's a multi-stage cooling process. First up is laser cooling. They use lasers to slow down the atoms, which basically means reducing their temperature. This technique itself was a Nobel Prize winner. After laser cooling, the atoms are trapped, usually by magnetic fields or more lasers. Then comes evaporative cooling. Think of it like blowing on hot coffee. The hottest atoms are allowed to escape the trap, which lowers the average energy and temperature of the ones left behind. They repeat this until the atoms reach that critical temperature for BEC, which is down in the nanokelvin range. Again, unbelievably cold. Once the BEC is formed, how do scientists know it's superfluid? They can poke and prod it. They might stir the condensate with laser beams to see if quantized vortices form, or to check if it flows without drag below that critical velocity. They can study how it expands when the trap is switched off, or how it interferes with another condensate, which shows off its wave-like nature. They've even done experiments on the International Space Station to watch BECs for longer in microgravity. The study of superfluidity in BECs is far from over. It's a super active area of research with tons of cool directions. There's quantum turbulence. Just like normal fluids can get turbulent, superfluids can too, creating a complex mess of quantized vortices. Understanding this is a big challenge. Scientists are also hunting for supersolids. Imagine a material that's both a structured solid and a frictionless superfluid at the same time. Sounds impossible, right? But dipolar BECs are looking like a good candidate for finding these. And just this year, in 2024, scientists made a BEC out of molecules for the first time. This opens up pathways to new kinds of superfluidity and quantum effects we haven't seen with atomic BECs. Then there are spin-orbit coupled BECs. By linking an atom's spin to its motion, researchers are finding exotic superfluid properties and new quantum phases, like stripe phases, where the material is part crystal, part superfluid. They can even create artificial magnetic fields for these neutral atoms, leading to new ways to make vortices without actually spinning the BEC. They're also looking into non-equilibrium superfluidity, seeing if superfluid phases can exist even above the speed of sound under certain driven conditions. How about atom lasers? Similar to optical lasers that give us a coherent beam of light, atom lasers produce a coherent beam of atoms from a BEC. These could be amazing for super precise measurements, atom interferometry, and even nanofabrication. BECs can also act as quantum simulators. They can be used to model really complex phenomena in other areas of physics, like understanding high-temperature superconductors, or even what goes on inside neutron stars. And because BECs are so sensitive to external forces, they're perfect for developing incredibly precise sensors for gravity, rotations, and magnetic fields. Some theories even suggest that the vacuum of space itself might be a kind of superfluid. So studying these systems helps us test the very foundations of quantum mechanics and maybe even find new physics. Now, it's not all smooth sailing. Creating and maintaining these ultra-cold systems is incredibly demanding experimentally, and the theories needed to describe them, especially when the atoms are strongly interacting or things are far from stable, can get super complex. Plus, directly seeing and manipulating things at these tiny energy scales requires constant innovation in experimental techniques. But the journey into the science of superfluidity and Bose-Einstein condensates has truly revolutionized how we understand matter at its most fundamental. What started as abstract theories has bloomed into a vibrant experimental field that's always pushing the limits of what we know. From the frictionless flow of atoms to the intricate dance of quantized vortices and the strange ripple of second sound, these quantum fluids give us a peek into a world governed by rules far weirder and more fascinating than our everyday experience can prepare us for. As scientists continue to explore this ultra-cold frontier, the promise of new discoveries and revolutionary technologies keeps beckoning. It's safe to say the science of superflow will keep us captivated for many years to come. Thanks for tuning in to G Fun Facts Online. Join us next time for more scientific adventures.